Hi guys, this is Dr. Edwards, again, I want to share with you today some information about ordinary differential equations, particularly second and third order differential equations with constant coefficients. Let me say firstly, these differential equations can always be solved analytically. And I think that's why I'm starting with these ordinary differential equations with constant coefficients. And then I'll come back to first order differential equations. After I give this particular video, I'll give another one on the first order kind. So let me get started. What you have here is the standard form of a differential equation with constant coefficients. It's written in this standard form. N can be any integer here. One, well, I'm going to start with 2. So if n is 2, this becomes a second order differential equation. If n is 3, a third order differential equation. And sometimes the quantity on the right hand side is 0. And other times it is not 0, as it is in this case. So this is called a forced ordinary differential equation, because not only do you have to solve the left-hand side firstly, but then once you get that, then you have to solve the left-hand side with the right-hand side. Okay, I think for the first set of problems I give to you, I'm going to have the right-hand side equal to 0 and get you practice on that kind of problem. All right, here's the reason that I'm starting with these is because the way we solve them, you can assume a valid solution. You substitute that into the differential equation and then solve for the unknowns. So this is what we do. So since y is the dependent variable, x is the independent variable here, you assume a solution of this form. Y equals e to the mx. So this is the regular e that you're used to seeing in your basic mathematics class. The reason we choose this is because, as you recall, the differential for e to any variable repeats itself. And that's the nature of this differential equation. So when you substitute this into this equation, you think about it, dy dx is equal to m e to the mx. D second y dx is m squared e to the mx. And so that's why it becomes convenient. So that's what you do. So you start out with both y and m being unknown. But in the process of solving the problem, you will emerge with specific values for m and y. Okay, let's go on. Here's an example then, which is a standard problem that you always get in basic physics. Is the simple harmonic oscillator or the Hooke's law with a spring. M is the mass of the oscillator. It is a second order differential equation. And since we're going to assume that the force constant force spring is a constant, then it becomes a second order differential equation with constant coefficients. All right, so you assume then a solution as I just indicated to you. And now you substitute that into the differential equation. And what you get then is an equation of this form. So once you solve the initial equation, which is this one, you get then that m is equal to plus or minus the square root of a sub 0. And a sub 0 in this case is k over m. Therefore, since m is plus or minus here, a sub 0, which is the square root of k over m. Then you can call one m1, call the other m2, and you get then two solutions. You assume some constant c1, e to the positive I omega t, plus some constant c2, e to the negative I omega t. Let's make sure you understand where the omega has come from. See, so since we have then that m is equal to plus or minus the square root of a sub 0, then m1, m2 is, and we let then the omega be equal to the square root of k over m. Therefore, this becomes the general solution to the differential equation. Now, it turns out that oftentimes the differential equation have initial conditions or boundary conditions. And if you have that situation, you can use those to figure out the values of the constants in front, C1 or C2. Sometimes these are called A and B, but that's okay. Capital A and capital B, but C1, C2 is just as good as N. What you do not see here directly is that with the use of the Euler's equation, e to the positive I omega t can be written in terms of cosines and sines. Therefore, this equation can be rewritten in the following manner. E to the, so y of t is c1 cosine of omega t plus c sub 2 sine of omega t. And this is the way it goes. It will be this way for every problem that you will to solve. Notice this was a second order differential equation here. If it's a third order, such as a couple of those that I've given for homework, this is a third order, third order, third order. This one is a second order. So I want you to go, now I think I only gave you two of these, 7.3.1, 7.3.4. So you go and work on these equations and let's see if you get a solution for these. Now let me indicate one other thing. Every time that you claim to have a valid solution to the differential equation, I will ask you to check to verify that it is indeed a valid solution. How do you check? Any quantity that you consider to be a valid solution, you substitute it back into the differential equation and you should get an identity. That is proof positive that you have a valid solution. So right here, if I wanted to verify that this is indeed, or here, both of these are the same, they're just written differently. Here they're written in e to the I omega t, or e to the negative I omega t, and here it's written in terms of sines and cosines. But you can differentiate y one time, differentiate it a second time, and then substitute the second derivative here, multiply that by the mass, equal to negative k times the y itself, and you should be able to simplify, and show that the left-hand side is equal to the right-hand side. You cancel everything out and you get 0 equals 0 or 1 equals 1. That is the kind of identity that I expect you to get when I ask you to verify that your supposed solution is indeed a valid solution. Okay, so that's what I wanted to say you to do. Let me now share another differential equation with you. So here, now this one now, so find and plot the solution of the ODE satisfying the given initial conditions. So time is considered to be the independent variable in this problem, and y again is the dependent variable. K is a value that's unknown at the moment, and capital A also is a quantity that's unknown at the moment. So this is the differential equation you have to solve. and it has two binary conditions. At t equals 0, y equals 0, and at t equal to 0, and at t equals 0, y prime is equal to 1. All right. So once again, you do just as I said previously. We're going to assume that this expression is a valid solution. Y equals a, e to the kt, and we're going to substitute this quantity into the differential equation. You substitute, you get then, and you can factor out capital A e to the kt, and you're left with this indicial equation that the quantity k squared plus 2k plus 3 must equal to 0. It must equal 0. You don't want this part to be 0, because if so, you don't have a solution at all. But it's okay to assign this part equal to 0. And when you do, you get then the specific values for k. So k now is no longer an unknown. So you see, this is a quadratic equation. You've seen that many times. And the coefficients, A is 1, B is 2, and C is 3. So you can solve this quadratic equation in its standard form. K equals minus B plus or minus the square root of B squared minus 4AC over 2A. So you go there, you substitute in the values, etc., and you get then two values for K. It can be equal to minus 2 plus or minus the square root, 2 times the square root of 2I over 2. And so we call them K1 and K2. And now you come here and you substitute then both of them into the differential equation. And you split up now, you say I have two A's. One, I call it A1, I call it 1A2. So this is a legitimate solution. You can stop right there if you don't have initial conditions to solve. But since we're going to solve this problem with initial conditions, let's go on and simplify it further, and we'll write the answer in terms of sines and cosines, which we've done here. So now we're going to go back and consider the initial conditions. At t equals 0, y equals 0. So you set y equals 0, and everywhere you have t, you put 0, and you grind it down, and you see that a1 is equal to negative a2. Follow through these steps. This is from the table of integrals I just put there so I can know how to differentiate. Since I know that the integral, the sine of theta d theta is negative cosine of theta, then I know all of the other expressions associated with integrating sines and cosines and differentiating sines and cosines. Let me see. So now we put that in. Now we have one other boundary, call them initial conditions when time is the independent variable, and that is y prime. Now y prime is equal to 1 at t equals 0. So I put 1 there and put 0 everywhere. And lo and behold, now this gives me a way of finding one of the two constants, a sub 2 in this case. So now that I know a sub 2, I also know a sub 1, which is negative a sub 2. Therefore, this becomes a valid solution for the differential equation. Now, if I tell you to show that it satisfies that means that you need to check it. You then differentiate equation and substitute it back into the equation, and you should get an identity. And that's what you get here. Therefore, this is indeed a valid solution to the differential equation, because here I'm showing that 0 equals 0. All right, that's what I wanted to share with you. Get busy on solving these differential equations that I've given to you. Have a good day.